In the previous section, we took a look at being able to approximate limits. And we were able to approximate limits by using a table of values. We were able to approximate limits by using graphs. They don't give us the actual values, though. So in this section, we're probably going to take the most important look at how to evaluate a limit, and that's by using analytic techniques. Now, analytic is just a fancy way of saying the exact way or the algebraic way. Okay, so algebraic, or we're not using, so no table, no graph. All right, so all we have to rely on is our brain and a piece of paper. All right, so that's what we mean by analytic, but it is going to give us the exact value. All right, so let's take a look at the different ways to be able to analytically evaluate limits. The first way that we're going to be looking at is by an easy direct substitution. Direct substitution means that the value that we're trying to find the limit of is within the domain. All right, so let's take a look at this first example. Lim as x approaches 3 of 2x minus 4. Well, this is a polynomial, and we know that anytime that you have a polynomial has its domain as all real numbers. So we can just go through and substitute. So this becomes 2 times 3 minus 4, which is going to be 6 minus 4, which is 2. All right, that's as easy as it gets. So you just tried, I'm going to abbreviate it DS for direct substitution. All right, a sneaky another one is this guy right here. All right, now some students might look at this and say, well, I can't evaluate that because it's a rational expression. But the only time when this rational expression is undefined is when x is 1/7. All right, now if you don't believe me, just go through and solve that. Clearly, 1/7 is not -1, so what we can do is we could just substitute. So we're going to use direct substitution, and we're going to say 5 times -1 squared plus 4 times -1 minus 1. And then in the denominator, we're going to have 7 times -1 minus 1. Now the denominator is easy, that's -8. We get 5 minus 4 minus 1. That just works out to be 0, I believe. And then finally, 0 over -8 by using numerical methods is just 0. All right. So just making sure that when you guys do these types of problems, the first step that you always want to try is direct substitution. All right. So if it works, you're done. If it doesn't work, you've only wasted like maybe a minute or two of your life. All right. Now, what if direct substitution is not possible? So let's take a look at a couple other examples. We have this limit. X approaches 13 of x squared minus 169 over x minus 13. Now, what if we tried direct substitution? Well, that would give us 13 squared minus 169 divided by 13 minus 13. This is 169. So we get 0 on top and 0 on bottom. And that doesn't make a lot of sense to us. Okay, 0 over 0 doesn't make any sense. And clearly, x equals 13 is not in the domain of this function. So does that mean that the limit doesn't exist? No, it just means that we have to use our second technique in which we're going to factor and simplify. Right, so we know that the numerator is a difference of squares, so we can factor this. So now our limit becomes x approaches 13, and by difference of squares, we know that that becomes x plus 13, x minus 13. And you probably remember from pre-calculus, once you simplify, you can cancel those out. And we're left with a really nice limit. We're left with lim as x approaches 13 of x plus 13. And now we can use our direct substitution. All right, so we get 13 plus 13, and that's 26. Right? Sometimes we don't have binomials, sometimes we have trinomials. So now we have this expression, x squared plus 9x plus 20 over x plus 5 as x approaches negative 5. Again, we're going to try direct substitution, but I think everybody can clearly see that negative 5 is not in the domain. So we get negative 5 squared just to try this out, plus 9 times negative 5 plus 20 divided by negative 5 plus 5. Doesn't even matter what the numerator is, even though we know the numerator is 25 minus 45 plus 20 is 0. And once again, that doesn't work for us. Okay, so what do? We factor. Okay, so the numerator is a factorable trinomial. So now we get lim as x approaches negative 5. Now notice, again, negative 5 is not 5 from the left. It's the actual value negative 5. Just to be clear, this is not the same as lim as x approaches 5 minus. Okay, so just be careful with that subtle notation. Right? They aren't the same. They look pretty close to being the same, but 5 minus is not the same as when x approaches negative 5. All right, so I know I sidetracked for just a second there. I just wanted to remind you guys of that subtle notation. All right, so let's get down to the factoring. We know that in the numerator that to build x squared, we need x and x. To build 20, it's either going to be 1 and 20, 2 and 10, or 4 and 5. And we know 4 plus 5 is 9. Everything's positive. And so it should look like that as the factorization. If you don't trust me, and you shouldn't because I'm a math teacher, then what you would do is you would FOIL it back out. All right. Just like we saw in the previous, now we can cancel out common factors, just like you did in pre-calculus. And now we have lim as x approaches negative 5 of x plus 4. We're going to now use direct substitution. Negative 5 plus 4 is indeed negative 1. Right. If you don't believe your answers, right? Well, first of all, you're going to use my math lab, and my math lab's here to tell you right or wrong. But what about in real life? How do you check? Well, you can go back to what we did in the previous section. You can use your table of values, or you can use your graph. In fact, let me just illustrate a check on this one. Now, we know that the limit is negative 1. All right, so here's what I'm going to do. Let me share the calculator really quickly. All right, and let me clear out this stuff. And I'm going to graph. Now remember, our function was x squared plus 9x plus 20. And we're dividing that by x plus 5. Now you might think that you're going to get some sort of quadratic function, because you probably remember from pre-calculus that, okay, well, you have a square. Anytime you have a polynomial square, you're going to get a quadratic out of it. Let's graph it. And we're going to resize the window. So we're going to hit zoom, and we're going to do a z standard. Okay, so 6. Oh, well, that's clearly not a quadratic. And even if I zoomed out, so zoom 3 and then enter, we get a linear function. Why do we get a linear function? Because remember, when we simplified it, okay, we ended up with a linear function. Okay, so I'm going to go back to the standard, Z6, and then what I'm going to do is I'm going to trace it. All right. And notice right here at 0, we get 4. But we don't care about that. We care about when x approaches negative 5. So what I'm going to do is I'm going to just trace this function until x gets to be negative 5. Or we could just do, I'll show you one last way to do it once we're done. All right, now at negative 5.1, it's negative 1.1. And then on the right side, negative 4.89 is going to be 0.893. So those are both pretty close to 1, right? We can zoom in here if we want to get a little bit more refined. So I'm going to zoom in. And notice that there's a hole here, okay? That's what we expect. So we're going to trace it a little bit more. All right, and we could zoom in again. Notice at -5, there's nothing, as it should be. And also, we're pretty close to -1. All right, so like we said, the analytic way gives us the exact value. But these graphs, they give us a pretty good idea of what to expect with the limit. Okay, so I would encourage you, if you're done going through and getting the analytic method, to utilize the graph of the function to be able to check what your solution might be. If they both indeed support one another, you're most likely correct. If one of them's off, then I would go back and check your analytic solution and then use a calculator to once again check again.